Hey everyone, I just wanted to make a video reviewing chain rule and going through a couple of examples. So let's get started with it. So recall that chain rule occurs whenever we have a composite function, like something in the form of y equals f of g of x. And I want you to remember that when you have a composite function, you have a function kind of inside of another function. So in this case, the outside function is going to be our function f, okay? And our function on the inside is going to be g of x, okay? So when I talk about the outside function, I'm talking about like what we have with f of x, and when I talk about the inside function, I'm talking g of x. Okay, so let's say that we wanted to take the derivative of our function y. Well, to do that, we take the derivative of our function f, but you need to remember that our function f, well, that's a function of g of x. So we're going to take the derivative of f as a function of g of x. So that's the derivative of the outside function, and we are going to multiply it by the derivative of the inside function. And since our inside function is g of x, we multiply by g prime of x. Okay, so this is how we write out the chain rule in Newton's notation. But of course, we could also write it out in Leibniz notation. So let's talk about how that would look like in Leibniz notation. You'll see me use Newton's notation most often, but Leibniz notation can also be used. So in Leibniz notation, we can define our composite function like this. So we have a function y, which is a function of u, right? So you can write that as y equals f of u. And we keep in mind that u is basically just the function g of x. Okay, so in this particular case, f of u, well, that's the outside function, and u equals g of x, well, that's my inside function. But this will all work the same way as it did with Newton's notation. So let's suppose we want to take the derivative. Well, that's dy by dx in Leibniz notation. And the way that that works is, well, we take the derivative of the outside function, but remember that the outside function in this case we write as a function of u. So the derivative of the outside function is df by du, and we're going to be multiplying that by the derivative of the inside function. Well, and since the inside function is g of x, we have dg by dx. Okay, so this is how you write this out in Leibniz notation. Great, so let's do some examples of actually using the chain rule, right? Because it probably looks more difficult than it actually is. Okay, so our first example. Let's say that if we have f of x equals 2 times 3x plus 1 all squared, find f prime of x. Okay, so in this case, it would be helpful to start by identifying what the outside function is and what the inside function is. So hopefully you can, you can take a look at this function and identify the inside function, but if you need a hand, most often the inside function is going to be written inside of a set of brackets. So in this case, our inside function is 3x plus 1. That's our inside function. Now the outside function is pretty much what's going to be left over, but I want you to think about what if we took our inside function and we just thought of it as being just x. So that is just like x, okay? That's how it's going to work, at least, when we're taking the derivative of our outside function. So we're going to be taking the derivative of the outside function almost as if we're taking the derivative of 2x squared. Okay, so let's see what this is going to look like then. So to find f prime of x, we have to start by taking the derivative of our outside function, which, remember, we're thinking of that in terms of like taking the derivative of 2x squared. And to do that, well, we take our exponent and we multiply that by our leading coefficient. So that's going to give us 4. And typically, if this actually was 2x squared, we would have, 4 times x to the power of 1. But I want you to remember that we don't really have an x here. We have 3x plus 1. So it's going to be 4 times 3x plus 1. And then we reduce the exponent of that by 1. Well, since it was 2, it's now an exponent of 1. So this is the derivative of the outside function. Now we need to multiply this by the derivative of the inside function. But notice that the inside function is 3x plus 1. So when we multiply by the derivative of our inside function, well, that's just 3. So we're going to be multiplying by 3. Okay, so now we can clean this up a little bit. I want you to notice that we have a 4 up front, and then we have a 3 at the end, right? And we're multiplying all these things. So we're going to have 4 times 3, which is 12, times 3x plus 1. And then I can distribute the 12 in, and we get 36x plus 12. So that is our derivative using chain rule. Okay, let's try another example then. So let's say I have y equals 2 over x cubed plus 4. Let's say I want to find the derivative, dy by dx. So I'm actually going to do this one in a couple of ways. But before we do that, it might actually be useful to rewrite this function so that it is more clearly a composite function. So how could I do that? Well, I want you to notice that x cubed plus 4 is on the bottom of like a fraction, right? So I want to bring it to the top and give it a negative exponent. So how would we do that? Well, we get 2 times x cubed plus 4 to the power of negative 1. Now it might be a little bit more clear how this is a composite function. So again, I'm going to do this in two different ways. I'm going to do it with Leibniz notation and I'm going to do it with Newton's notation. So I'm just going to kind of split the page in two here. All right, so let's set this up with Leibniz notation. So with Leibniz notation, right, we have a function of u, and u is basically g of x. So I want you to recognize that our g of x, which is our inside function, well, that's going to be what's in the brackets, x cubed plus 4. So that is our inside function. Okay, our outside function, which is f of u, right, is going to be like, I took my inside function, which is x cubed plus 4, and I called that u instead. So that would be like 2u to the power of negative 1. Okay, so remember that the derivative the derivative of a composite function in Leibniz notation, so the chain rule in Leibniz notation, is dy by dx equals df by du times dg by dx. Okay, so we're calculating dy by dx. So that means we need to know df by du and dg by dx. Well, df by du just means the derivative of the function f with respect to u, and dg by dx means the derivative of the function g with respect to x. So let's start with finding the derivative of f with respect to u. Okay, well, we take a look at our function f, which is with respect to u, which is given up here, right? And I need to take the derivative of that with respect to u. So I take the negative 1 and I multiply it by my 2 up front. So I get 2 times negative 1 is negative 2. And then I reduce the exponent on u by one whole value. So that gives me negative 2u to the power of negative 2. So that is my derivative of f with respect to u. I'm going to multiply that by the derivative of g with respect to x. Well, my function g is given right here. So I take the derivative of that with respect to x, and I'm multiplying. So the derivative of this function with respect to x, well, that is 3x squared. Okay, so now I have negative 2u to the power of negative 2 times 3x squared. So let me clean this up a little bit. So the negative 2 multiplied by the 3, well, that gives me negative 6. Okay, I've got an x squared up top. And then, of course, I have u to the power of negative 2 to deal with. Well, since it's a negative exponent, that's going to go on the bottom. So I get negative 6x squared over u squared. Now, I want you to remember that u is basically just our function g of x. So what I can do now is I can actually replace the u here with x cubed plus 4. So what's that going to look like? Well, we will get negative 6x squared over x cubed plus 4 squared. And that is the derivative of our function, at least in Leibniz notation. So let's say I wanted to do this same thing in Newton's notation. Okay, well, in Newton's notation, remember we're calculating y prime. So we need to identify the inside function and the outside function again. Well, the inside function is still x cubed plus 4, which means that I'm thinking of my outside function as being like 2x to the power of negative 1, or at least that's how I'm going to be taking my derivative similarly to how I do that. So I take the negative 1, I multiply that by my leading coefficient, which gives me negative 2. All right, then we have x to the power of 3 plus 4, and then I have to reduce that exponent by a whole value, so that gives me to the power of negative 2. Okay, that is the derivative of my outside function. Now I have to multiply by the derivative of my inside function, which in this case is going to be 3x squared. So now we can clean this up a little bit. So I want you to notice that I have a factor of -2, that's going to stay up top. I've got a factor of 3x squared, that's going to stay up top. And then I've got x cubed plus 4 to the power of -2. Well, since it's a negative exponent, I know that's going to go to the bottom. So let's see here. I can write x cubed plus 4 to the power of 2 on the bottom, so I can write it with a positive exponent. I know I have a factor of -2 and a factor of 3x squared that goes up top, so when I multiply those, I get -6x squared. And notice that that is exactly the same thing that we got in our Leibniz notation. Okay, so let's try one more example. This time I'm just going to do it in Newton's notation. So let's say I have y equals -4 over the cube root of x cubed plus 1, and I'm trying to find y prime. Okay, so again, it would probably be a good idea to write this so it's more clearly a composite function. All right, so let's see. I'm going to write my cube root as a power of 1/3, and now I'm going to use a negative exponent to bring all that stuff in the denominator up top. So we have -4 times x cubed plus 1 to the power of -1/3. Okay, so I want you to identify that the inside function is x cubed plus 1. And so the outside function would be like almost like -4x to the power of -1/3, or at least that's how we'll be treating the derivative of the outside function. Okay. So let's take the derivative of our function. Well, it's equal to the derivative of the outside function, which again, we're treating like -4x to the power of -1/3. So I take the power of -1/3, I multiply it out by my leading coefficient, so -4 times -1/3, well, that's positive 4/3, right? Then I take x cubed plus 1, and I reduce its exponent by one whole value. Well, -1/3 subtract 1 is -4/3. Okay, so this is the derivative of my outside function. I need to multiply now by the derivative of my inside function. Well, the derivative of x cubed plus 1 is 3x squared. Okay, so now I can clean this up a little bit. I notice that I've got a factor of 4 and a factor of 3x squared that's going to stay in the top of my fraction. I've got a factor of 3 that's going to be in the bottom. And then I've got x cubed plus 1 to the power of -4/3. Well, that negative exponent means that's going to the bottom too. So let's see. Let's deal with the bottom first. I've got my factor of 3. Then I have x cubed plus 1 to the power of positive 4/3. I've got a factor of 4 up top and a factor of 3x squared. Well, those are going to multiply, and I'm going to get 12x squared up top. And then lastly, I want you to notice that I've got 12 up top and a factor of 3 on the bottom. Well, I've got a common factor of 3 there, which I can cancel out. So I'm now going to have 4x squared over x cubed plus 1 to the power of 4/3. And that is the derivative of this function. So I hope that this video has been useful. If you're still unsure about any of this, you can come talk to me in class. But I guess not till tomorrow, so take care, guys.